Alright, so let's look to reduce this. So with these steps, as we continue, some of the stuff that you had to add in will be for the generators. They normally, the magnitude and the phase of it, I think I mentioned in previous videos, will always be 1 angle 0 degrees. Yeah, all these are represented in per units. So you can write per units next to each of them. And they all represented in terms of G, but the J will come further down when we actually calculating the fault currents. So, but if you want to, you could put the J, and probably you should, because that's how normally they write it. Right, so we have all the impedances. So the next thing we have to do is reduce it to get this part, the equivalent impedance between the generators and the location of the fault. So this whole thing in the middle here had to reduce. So everything here have to reduce to 1 impedance. So the first thing I like to do is look for the stuff that are in series. So I'll just draw over the neutral for now. Now let's try and see if we could find anything that is in series. So you zoom in. So from a generator, this impedance is in series with this impedance going to bus 4. Then this impedance is in series with this impedance going to bus 4. So these two here are in series with, and these two are in series. So we could add those two together to bring it on. So we'll do this one first. So you have the generator, 1 angle 0, coming down to 1 impedance. And the sum of those impedances will be 1 plus 0.02348. Yeah, because there's 1 here adding with this. So you'll end up with 1.02348. And that ending at 5. So the whole thing there will give you the ending at bus 4. So your next piece, so you have, so this one here, you have to keep it there, because for now, it's splitting into these two, so it's not really in series with these as yet. So these two will be in series, so you have to come down with the generator, keep the 1, and then from this one now, it going through this and this. So if you add those two, 0.037 plus 0.063, you get 0.1, and that is the impedance connecting this bus here to 4, then this bus 1 to bus 4. Alright, so these two are in series. Cool. I don't know. Since we combine those two, well, we could draw over these two coming down. So from 1 to 2 and then 4 to 2. So go back our faulted bus. So 1 to 2 and 4 to 2. So 1 to 2 was 0.049. And this one was 0.0377. Okay, cool. So now we kinda at a standstill, but we should. So the other thing that they will bring is something called delta to star conversion. So that's something to look out for. So anytime you're realizing that it basically in this point you cannot reduce it anymore in the current form, so you have to convert all the delta formations to star formation. So right now we have two, just have to choose one. So these three at the bottom here giving you a delta because this bus bar is 1 point, so technically these two connected. So you kind of getting this kind of shape going on at the bottom, or you could do it with the top because these generators here are connected to the same neutral point. So you kind of have this pattern going on top with the two generators and then this 0.1 at the bottom. Yeah, so we'll wanna convert this. So for now I'll use the top piece. So we're converting this top piece from the delta to the star. So what I like to do is put a dot, put a dot, and put a dot, and I'll just draw in the resistors that I expect to have. So technically, if you want to set up it quite at the top, you could put it at the bottom, like here. So it's only the generator on top. So you can just put the dot here. Right, so it wouldn't change the difference. So this is the first one. Then we have one at the bottom. So since we want to convert it to the star, we put a dot in the middle. So there's the first impedance. Then we have a next one going here. And then we have a next one going there. So that will be the result when we convert these three into a star. So we could do it one by one. So the easiest way to do it or to make the conversion, so let's just draw the two. So for now, since these two generators, so here we forgot our 1 angle 0 here. So since these two generators connected to the same bus potential, we could just combine it to one. Right? So basically we need this, this, and this. So let's see how to get it. So the first one, the trick is to know what this will be, is this the product of the two impedance connecting to the dot divided by the sum of all three impedances. So in this case, this dot here, technically this connecting to here, and this one connecting to here. So it will be 1 multiplied by 1.02348, and you'll have to divide it by the sum of all of them. So it'll be 1 plus 0.1 plus 1.02348. So you end up with, on this one here, it will be 0.5 4819. Right, and then this bottom one here. So since you already have it in a calculator, the sum wouldn't change, so the top piece. So in this case, the two that connect into here will be this one and the 0.1. So that's going to multiply by 0.1, and you'll end up with 0.04819. And then this one in corner here will be the 1 by the 0.1. So it'll be 0.047. And then we just add back in the rest of the circuit. So since the connection points with these two, so this combine and go on to make the star, and this is drawing these two back. So that was 0.049. And this one here, well, that was 0.0377. Yeah, then draw back in a bus and a fault. So now we clearly seeing things coming together. So these two are in series, and these two are in series, so we can do another reduction. So just gonna keep reducing it until they end up with 1. So generator, don't forget to pay 1 at the 0. And this coming down to 1. So that was 0.4819. Then we have the sum of the two equivalents. So this piece, when you add these two together, so it have a split. So it'll be 0.096 J per unit, and then this piece it will be 0.086 J per unit. So I'm rounding off a lot. So if your answer is kind of looking off, because I round. So you don't try not to round too much, because the more you round, the further away you will go from the actual answer or the exact answer. So try to keep all the decimal places as far as possible. Alright, so 1 or 2 more steps. So these two are in parallel with each other and will be in series with this. So product over sum for that. So 0.4819G. And then because it's in parallel, to reduce it to 1 will be the product of the two divided by the sum of the two. So it'll be 0.096 multiplied by 0.086 divided by 0.096 plus 0.086, and you'll just end up with the answer being, when you add the two, and product will be 0.04555J per unit. And then finally, when we add the two together, we end up with the generator and the two impedances. When you add those two, the series should be around 0.525J per unit. And then we have the fault, which is what we wanted to do. And that'll be equivalent. So now if you want to actually get the per unit fault current. So I short circuits per unit is 1 on Z per unit, the equivalent. So that'll be 1 on 0.525 J. And it should end up with negative 1 point, let's put in my calculator, 1 divided by 0.525 J. So negative 1.904 J per unit. Right, and then MVA short circuit is equal to V per unit multiplied by I short circuit per unit, and since this is 1, this will also equal to minus 1.904 J per unit. In this case will be MVA. Yeah, because this is MVA short circuit. And this is amps. Cool. And then if we want the actual value, no pun intended, we'll need to multiply each by its base. So I'll need to find what I base is. So I base is the MVA base divided by root 3 by voltage base. So the MVA for the system was 100, and then root 3. To get what the voltage base is, we need to see what voltage is attached to the bus. So we have to go back to the system, and since it's bus 2, the transformer is a step down transformer. So the voltage of this bus 2 will be 230, because a 230 rated bus. Yeah, somewhere around. Yeah, it'll be a 230 rated bus. They will give you it. Most of the time you will know. But I believe this transformer stepping down to 230 volts. So the voltage or the nominal voltage of this bus will be 230. So kV. So just write 230 here. There's MVA. So when you do the maths, so it'll be 100 mega divided by root 3, 230 K. And when you do the math, you'll get 251.02 amps. So now, if you want the actual fault current, which is really what we want, any day, so it'll be I actual will equal to I short circuit per unit multiplied by a base. So that'll equal to minus 1.904 J per unit by 251.02. Put in the calculator. 1.904 multiplied by 251.02, and we end up with 477.94 amps, 3 amps. So that would be the actual fault currents. And if we go back to our system faults, and we put a bus faults, and let's make it 3-phase bus fault at bus 2, and we calculate it. So So the actual, well, the calculated or simulated, if you want to be specific, answer is 476, and we got 477. So if we were to not round so much, we'll actually get the answer closer to what was simulated in Power. Okay. If we wanted the MVA actual, since the MVA base is 100 mega, you would just have to multiply this value per unit MVA by the MVA base to get the MVA actual. Okay, but this is the fault current. The fault current is just 477.94 amps, which is more than what we got in Power because we rounded a lot. Okay, so that's basically a run through of a typical question, right? Apologies for the minor mathematical errors that may be here, but the process will be the same. Alright, so it was helpful and we'll speak in the next one.